Swayam Prabha. Digital India. Educated India.
Good morning. So, today we will look a bit more closely in magnetic circuits. I would say that the material is not really new. You are already aware of Faraday's laws, flux, magnetic field intensity, flux density, Faraday's laws of magnetic induction, terms like flux linkage, rate of change of flux causes induced EMF, Lenz's law, which is that the direction of the EMF induced, which is given by the Faraday's law is such so as to oppose the rate of change. So, you are reasonably well aware of these concepts. Iron or a ferromagnetic material has magnetic dipoles, and such dipoles usually cause an increase in the flux density when you use a magnetic material. So, you have seen magnets, you have seen electromagnetic magnets, you have seen compass, you have seen how a magnet attracts filings, you have seen magnets being used, for example, as a sticking material in a refrigerator door or on many other such kind of gadgets. Even here on my iPad, you can see that the pencil attaches to the frame using a strong magnetic field or coupling. So you have seen permanent magnets. So we have both studied, and in practice also we have seen many applications of the magnetic circuits, magnets. Today the main important possibly concept which we are going to introduce from an engineering perspective is to treat magnets as circuits. We are used to electrical circuits. We have seen resistances, inductances, capacitances, we have written their circuits, we have solved those circuits using differential equations, we have done many things with it. But in your earlier background in the 12th, 11th and 12th in the school, you may not have come across treating also the magnetic elements through circuit analysis. The idea is to create analogous treatment to what we have in the electrical circuits, that is, instead of resistances you would have here reluctances, instead of voltage sources or EMFs you would have you will have MMFs or magnetic motive forces. You will have analogues of Kirchhoff's current law, which is here it would be related to flux, which is going to be the replica or analog of current, MMF, which is the replica or analog of voltage, and the Ampere's law, which also you have studied earlier as a replica of creating the analog of Kirchhoff's voltage law. So in some sense this lecture tries to take advantage of your knowledge of electrical circuits and tries to show that many geometries can be well defined, many well defined geometries where the flux paths are very nicely and well defined can be treated analogously as magnetic circuits. In the process, we will also review Ampere's law. In the process, we will also review Faraday's law of electromagnetic induction and the right hand screw rule, the Lenz law. So, our most of those concepts will also be brushed or revised. So, let us start with the Ampere's law first. The Ampere's law says that if let's look at this geometry here, which is a closed toroid. The flux is, if you look at the cross section here, this is a top view of this geometry, but there is a complete cross section sitting here, which is having a width of W and a depth of D. And so, the area of cross section that these flux lines are going to face, the area of cross section is AC which is D into W. Now, I have wound turns of a coil here in this particular fashion, and if you take a right handed screw, okay, and move it in the direction of the current. So, you will see that if I move it in the direction of the current, this right handed screw, it moves forward. So, it shows, it means that the flux is going to be built up in this circular fashion, provided the current is entering the coil in the direction which I have indicated. And for this you require either to connect a battery or some other voltage source. It has to be connected, and then this current flow will be set up. I have assumed here that the core is ferrite. This is because of the fact that you get good magnetic field or good flux values or good B's flux in densities when you use a ferrite core. If you want to set up the same B in air, as you will see later, you would need far higher values of the current to set it up. We will come to that. Let us say, we are going to use also a terminology called I net, the net current, which is basically the number of turns times the current. Now, the reason for this is, suppose I have one turn like this and it sets some flux of phi. If I replicate n number of turns like this, then each one of them will cause the flux to increase, and superposition therefore says that the flux which will be set up in the core would be n times of phi, which is also called as magnetic flux linkage. And so this is effectively as good as saying that the current has been multiplied n number of times. So, therefore, I net is which is same as Ni, and another name for this soon you will see is magnetomotive force or MMF. Now, what does the Ampere's law say? Ampere's law says that the magnetic field intensity, if it is H, then H times dl. So, here is the direction in which H is acting, and this is also the direction of dl. Here the H is acting like this, and the dl direction is also like this. So, if you do a superposition of H into dl over a closed path, this is the closed integral which I have shown here, then this should be equal to I net, which is the number of turns times I. So, the unit of I is amperes, number of turns is obviously a dimensionless quantity, but so strictly speaking, from a physics perspective, the unit of Ni is just amperes, but in engineering usually we like to call it as ampere turns. Of course, turns is dimensionless, it is a slightly more descriptive term is all I would say. So, the Ampere's law says that the dot product of H dot H and dl taken over a closed path H into dl is equal to the net current which is enclosed, which is equal to n times of I. Now, if you are using a magnetic material, then if you are using a magnetic material, then if you are in, let us say first you are in air or vacuum, then what happens is the flux density, whose unit is Weber per meter square, where Weber is the amount of flux and meter square is the area of cross section, or also called as Tesla, also is called as Tesla, would give you a B which is mu 0 times of H, where mu 0 is the permeability of the iron, not the iron, the vacuum or air. Vacuum or air, they are basically having the same permeability, and this constant is really small. So, even whatever I have shown in the whatever I have drawn here, I would say is kind of exaggerated only. This is also kind of exaggerated only. The constant is really small, 4 pi into 10 to the power 10 to the power minus 7, and this is the slope of the BH line. But if you use a iron core as I just showed, or a ferrite core as I just showed you now, then what is going to happen is that this line, this B will be amplified or increased significantly. So for example, this could be when the ferrite core has a relative permeability of 10,000. So, then in ferrite, if such is the ferrite core, you will get mu 0 mu r times of H, which is in this particular case 10,000 times B that you would have got in air or vacuum. So, the flux, if the flux density increases, then B dot ds, the area of cross section, and the flux density is basically, this is the flux. So, obviously, the flux will be increased, the magnetic flux will be increased, and since the Faraday's law says that the induced EMF is proportional to the rate of change of flux, and if there are n number of turns, then the additive effect of those number of turns will cause the, so d phi by dt will turn out to be my EMF per turn, and if you sum it over for many number of turns, then this will become the induced EMF, which would be same as minus of d by dt. I can write it as n phi, which is then also called as flux linkage, and so the induced EMF is minus d psi by dt, and this minus sign, if you would recall what you have learnt in your 11th and 12th when you studied magnetic circuits, is comes from the Lenz's law, which says that the induced EMF will be such so as to oppose the rate of change. So, for example, just to give you an example, let us say that I had a sorry. Let us say that I had a circuit like this. Let me, I am just drawing a, let me group it, yeah, and duplicate it and make it a bit shorter, and let me keep it here. Okay. So, what I have got here is, let us say a iron core like this, and I wind turns on it like this, and let us say that I connect through a switch a battery like this, and when I close the switch, it tries to push the current I through the magnetic circuit. So, again, if this is the way in which current is being pushed in, if I move the right handed screw, it will tend to move these lines forward. So, I am going to set up a flux path. So, I am going to set up a flux path which is going to be magnetic flux lines, which are going to look like the ones the way I have shown it here now, and this is the iron core. So, the voltage source is plus and minus, this is the plus and minus. Let us say that somewhere here there was also a resistance. Usually there would be some resistance, you cannot have paths which are free of resistances unless you use superconductors. Then you would have a resistance like this, and following the same convention, we will assume that all voltages which are either induced or applied, they are all additive in nature, then this is the induced EMF. So, now if you look at it, if you look at what I have done here, if the induced EMF was additive, the means the basic convention that I have used is a additive one. So, let us say if this was 10 volts and let us say this was 1 volt, and let us say that this 10 volt is causing a current of let us say 1 amperes, which is causing some x amount of flux in the x amount of flux or x amount of Webers in the magnetic circuit. Then if this induced EMF, let us say which is 1 volt, is in the direction like this, then it will cause a current of 0.1 amperes and would therefore lead to 1.1 times 1.1 times of the net flux. It will rather lead to 0.1 it will lead to 0.1 x times of the flux it will create in the core, because if the current is increased, the flux has to increase, and so the flux will become 1.1 x Weber. Now, this seems to be a condition like a avalanche kind of a condition, which will cause finally this kind of a growth will basically cause the flux to go to infinity, which physically does not make sense. So, what the Lenz law says, is that the flux has to be, the current, the induced EMF has to be in such a way, so as to oppose this change, and therefore, if this is the way I have written this is the convention which I have used for induced EMF, then actually the voltages should be the other way round and not trying to increase, but it should actually be it should actually lead to minus 1 volts and to so that the net voltage will tend to sort of oppose it, and to get this minus volts here, what we say is we just introduce this negative sign here. So one turn creates a EMF which is proportional to d phi by dt, n turns creates induces a voltage which is proportional to n d phi by dt, and then with this taken as the polarity convention in the algebra here, a minus has to be introduced, and so many places you will find the induced EMF to be written in this particular form, E equal to minus n d phi by dt. But now suppose instead I directly mark plus and minus E like this here. So, if I mark plus and minus E like this here, then what is going to happen? It means that this induced EMF which is going to be set up is going to cause a current which will try to flow in this particular opposite way, that is, it will try to cancel this particular rate of change, that is the current which is trying to be forced by the source from applied. So, automatically it is opposing it. So, if I mark the polarity of EMF like this, which is same as this is plus minus V, V is equal to E, in that case I do not need this minus sign. Because my polarity marking is already minus of E, and minus of E has been shown here by changing the directions of the plus and minus related to E, and therefore, this becomes n d phi by dt, which can also be written as V times, I can take the n inside, d by dt of n times of phi, or V equal to d psi by dt, and usually I mean I am slightly stepping a bit forward, but this is connected to the current, this flux linkage is connected, is also to some extent we all know this, that the flux linkage is written as inductance times of current, and if the inductance is constant, then we will write V equal to L d I by dt. So, this is the most common representation of the applied voltage as plus d psi by dt or L times d I by dt. This is the way you will find it in all circuit analysis textbooks, in all engineering textbooks. So, you should understand that what you have earlier learnt in schools, which is E equal to minus n d phi by dt, that is correct, absolutely right, but it was based upon a convention that all voltages, whether applied or induced, are written in a additive sense when you circle around the loop, but then this is bit cumbersome to carry this minus sign everywhere. It is also called as a generator convention, and it is bit cumbersome to carry this minus sign everywhere. So, what we usually do is we flip the signs as I have shown here. We flip these signs of the polarity markings of the E. So, now V and E are not additive. E is now shown as countering already by its sign convention, it is shown as countering the V, in which case we can drop this minus sign in n d phi by dt. That is not to say that we are violating Lenz's law or anything like that, but now we have a representation which is V equal to d psi by dt, which can, if the inductance is constant, can also be written as V L di by dt. This is a very, very basic and important point, and I think it is good that we cleared it very, very early in the course. Now, again coming back to the BH circuit, why do we use the ferrite core or any iron kind of material? That is because these materials are having inside them dipoles, which you can also call magnetic dipoles, which you can write them as north and south. And if you apply, let us say I am sorry, if you apply, let us say, a B or a H like this, then what is going to happen is these dipoles will rotate, and there is of course a space restriction inside the material. There is lot of empty space also, and then there is a strong there is a space restriction also. So, you will find some friction which will also which will be faced. So, there would be some heat energy also dissipated in the process of this realignment, but they will align now, they will tend to align in this way. All of them will, these magnetic dipoles which are there inside the ferrite as it is, will align with respect to the magnetic field. And so, if you put so many small magnetic elements parallel to the H which you have applied, then effectively what will happen? If this H was creating only B mu 0 H, each one of them is going to basically add to the B which is being created, and therefore, the B in the ferrite core will become mu 0 mu r H, and this mu r could be a very large number like 10,000 or so. And so, the magnetic field, so the BH line, BH line would be would be, as I have shown in the figure, if with a ferrite core, would be having a much higher slope. The slope here is, this is mu r equal to 1. So, we say that in air or vacuum relative permeability is 1. So, the slope here is mu naught, and the slope here is mu r mu naught. In a extremely ideal kind of a situation, if you want to think of a ideal ferrite magnet, then you can imagine that mu r is going to infinity, and that I have superposed here by the blue line here. If you want, I can make it a bit thicker to sort of emphasize it. Then as the mu r keeps increasing, what is happening is, this is your original line. Now, you increase mu r further, you increase further, you increase further, finally, it will come parallel to this line. So, in a very idealized situation, mu r will tend to infinity, and the B will just become, the BH curve will become just the vertical straight line. Understand that this is just a conceptual idealization of some ferrite core which is linear in nature and so on and so forth, but in actual practice it will not be such. It will not be such. In such a ferrite core, if I want to set up some magnetic field, then as per Ampere law, I should require n times of I. But now look at this. Let us say this is my ferrite core, like the way I was having earlier. Now, for such a ferrite, if B is what is the current that is required to set up any flux? If it is actually a clear cut vertical line like this, any flux which is required, of course, can be set with zero current. So, you will not require any current to basically set up this flux. So, for example, if V is voltage applied, if assume that this V is voltage which is applied, then V will become equal to, we saw that it will be d psi by dt. So, n d phi by dt. So, if for example, suppose I apply a V as a sinusoid, initial condition is 0 flux, then as I keep integrating this V dt, I will keep on getting the value of phi of t, which will be integrated from 0 to t. So, I will get a value of phi of t which will come from here. If the V of t is a sinusoid, then integration of sinusoid is a cosinusoid. So, I will get a waveform which looks more like a cosinusoid, and the flux definition will come from here. So, some way there will have to be a definition of flux which is coming, but the flux, but the current which would be required to set it up would still be 0. So, this is a kind of a philosophy that you can try to capture here, is that usually what is the flux which is being set up? We usually use this equation V equal to d psi by dt or n d phi by dt with initial condition on the flux available in the circuit, magnetic circuit. We use that to find out what is the flux. Once the flux is find out, then basically you divide it by the area of cross section, you will get B. Once you divide the area of cross section, then you divide it by mu 0 mu r, then you will get H. But what is H? H is basically amperes per meter, so magnetic field intensity. So, once you know the current, once you know the length of the magnetic circuit, the flux lines, what path they are following, then the H times of L will become the N of I, and knowing N, you will actually know what is the current which is required to set up this flux. This is essentially the essence of the way Ampere's law is applied. So, let me get back now to that Ampere's law which I want to use now. And so, we have now said that H times of dl is equal to n times of I, which is I net. I can write, instead of H, I can write B by mu 0 mu r. This is assuming that it is a linear material. Non-linearities we will discuss later on. Iron is not a linear material, but B divided by mu 0 mu r, B times of dl will become n of I, and direction of B and direction of H are same, because B equal to mu 0 mu r H. Mu 0 is a positive scalar, mu r is a positive scalar with ferrite materials. And so, now in this particular case, if I take a middle line and close it, that is a mean path, and I can use for this magnetic circuit. Actually, the length of the path keeps changing if I change the radius, but roughly I can take as an approximation, I can go through the mean path, and I can write therefore B times the length of this mean path is going to be 2 pi r, and the H and dr or dl elements have an angle 0. So, cos theta is 1. So, theta is 0, cos theta is 1. So, B times of 2 pi r will be equal to mu 0 mu r n I, and so the flux which is B times of AC, B will come out as mu 0 mu r by 2 pi r times so B will come as mu 0 mu r by 2 pi r times of n of I should be multiplied by AC, and so the flux becomes equal to this particular value which I have shown here. Now, this, as I said earlier to you, n of I is called as the MMF. So, this is the MMF. If I divide it by the flux phi, then what do I get? I get a quantity which only depends upon the geometry of my simple magnetic circuit. So, it is that is nothing but 1 by mu 0 mu r L by A, and what would be the unit of it? The unit of it would be MMF is Ni, I called it as ampere turns, flux is in Webers. So, the unit of this is going to be ampere turns per Weber. Now, this, as I said, N of I, which is the cause for setting the flux. So, the in electrical circuit EMF or voltage is the cause for causing the current. So, here the MMF is the cause. Consequence in a electrical circuit, the voltage causes current to flow, here the MMF causes flux to flow, and there is some opposition which is seen in the electrical circuit to setting up of the current, that is called as resistance. Similarly, here there is a certain reluctance, if not resistance, there is it is not directly a lossy element like a resistance is, but there is a reluctance you can imagine to setting up the flux, otherwise the flux would go to infinity, and that reluctance is. So, this quantity analogous to resistance is called as reluctance. So, we get a very interesting relationship which is the analog of your Ohm's law for magnetic circuits, simple magnetic geometries, which is that MMF is equal to reluctance into flux, and here in the resistance we had rho 0. For example, if rho is the resistivity of the wire, and you would get the resistance as rho times of L by A, while here you get something very similar, the reluctance is coming out to be 1 by mu 0 mu r, which replaces the rho constant here, and the other term L by A, the geometric part of it seems to come out in a similar way. So, you really see we have developed an analog of Ohm's law. Now, once we have developed the analog of Ohm's law, then naturally the question comes to you what about KCL, what about KVL, is the Kirchhoff's current law valid, is the Kirchhoff's current voltage law valid. So, let us look at this. I have taken another geometry here. In this geometry, this is a magnetic core, and I have wound the turns similar way, turns on the central limb. There are two side limbs, one central limb and one top and bottom limb. The use of this geometry is that basically the flux which is being set up here, I am able to break it into two parts, usually equal parts, and bring it back in this direction, in this way. So, if the flux set up here is phi, then because the flux lines cannot accumulate, they have to keep flowing. So, they will either break here or they have to flow like this, and therefore, if I think of this as a junction, I can say that the flux entering this junction is equal to the flux leaving this junction, which is essentially the statement of Kirchhoff's equivalent current statement of Kirchhoff's current law, which did not allow charge to be accumulated at a junction and the charge had to flow. So, if the charge is coming to a junction, which is the current which is coming to the junction, then the same the charge has to dissipate out without accumulating at the junction. So, therefore, the net current which is entering the junction is equal to the net current which is flowing out of the junction, or the algebraic sum of the currents at a junction is 0. Similarly, here algebraic sum of the fluxes at any of these junctions is going to be equal to 0. So, the KCLs can be applied at these loads. Now, look at this, what is the cause? The MMF. So, the cause I have put it here, MMF plus minus N of I. Now, first thing is, when I try to set up the, let me take a loop like this, let me take a trip, closed trip like this. This cause, the MMF Ni, when it goes through this part of it, would expend, you will expend an MMF which is equal to H times of L in the central limb, then you will expend some H times of L in the side upper limb, then you will expend some H times of L in the in this particular limb, and then you will expend some H times of L in this particular limb, and then you would have returned to the original position. So, all that you would have expended is actually nothing but the MMF which you have applied, the cause which you have applied, which is shown here. Now, what is expended? What is expended can be written as reluctance times of the flux. The flux is already flowing here. So, the central part will just impose a reluctance R1 to it, then the upper side half will impose some reluctance R2, and this the side limb here will then enclose, let us say, a reluctance R3, and then finally the bottom limb will enclose will impose a reluctance of again R2 by the symmetry, and then the other part of it is moving like this. So, therefore, I have taken a symmetric construction. So, I will get again R2, 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 and now what is this? This is exactly an analog of a electrical circuit where the voltage source has been replaced by MMF and the resistances have been replaced by reluctances, and since the laws are identical, since the Ohm's law also has a very similar or analogous or almost identical form. So, therefore, you can very quickly, using the same set of reasoning, come to the conclusion that just like in a series circuit the resistances are added, the reluctances will be added in a series circuit, and just like the resistances when they are in parallel, then the reciprocal of the resistances are added to get the reciprocal of the net resistance. Similarly, if the reluctances are in parallel, then the reciprocal of the reluctances will be added to get the reciprocal of the net reluctance. So, with this, I think you would really appreciate that this is a beautiful simple way of treating magnetic circuits, reusing the knowledge of what we have in the electrical circuits. So, now let me take a example. This is motivated from, I think this example is somewhere there in electrical technology by Hughes, one of the earlier books, if I am not, there are many editions of it. There are many wonderful books available on this subject. Hughes is one of them. I like it a lot. When I was a student also, I studied from it. There was a British library close by, and I used to go and read it there. Then there is a beautiful book called Electrical Machinery by Fitzgerald and Kingsley, and there are again many editions of that book also. And then you have a very good book of from M.G. Say on electrical machines, and then I think Nagarath Kothari has a wonderful book. So, there are plenty of books available to read this subject, and you are free to choose whichever you like. Let me illustrate the application now. Let me illustrate to you the application of this magnetic circuit here. I have a geometry shown here. Okay, I have a geometry which is shown here. There is a small air gap of 1 mm and the coil is wound on the central limb. It sets up a flux like this, which will come back through the air gap. It will go like this and again come back through the air gap like this. Now, what the central section has a area of cross section of 800 square, and the other outer sections have 500 square, and the number of turns are 500, and I want to set up a flux of 1.3 milliweber, that is 1.3 into 10 to the power minus 3 Weber in the central limb, and that flux is obviously going to also pass through the air gap. And usually we talk of some leakage of flux, because flux is once the mu r is finite, then everything will not just stay inside like this, but some flux will also, you can take each of these loops and try to find out what is the H dot dl acting on it, and according to that H dot dl, and you can find out what is the reluctance associated with it, and then you will know what is the flux which is going to flow because of that, and then you will know what is the B which is going to flow like that. So, basically what I am trying to say is that there will be leakage, but because the mu r's are like 10,000 times more with ferrites than air. So, the leakage is a parasitic effect unless deliberately created, and we will ignore that in our initial discussions. Similarly, there is a bulging out of flux lines on the at the air gap. There will be a bulging of the flux lines, and the bulging, what advantage does the bulging provide? Reduces the reluctance. The area of cross section increases, reluctance reduces, MMF reduces, which is how the natures will try to work, that it will try to create flux lines in such a way that the cause is not expending unnecessary effort. But in our case, in this particular example, what we are going to do is ignore the fringing, as this effect is called, the fringing near the air gap. Fringing will be seen only near the air gap. If you have to account for fringing, you would usually be told take 10% extra area of cross section or 5% extra area of cross section to account for fringing in the air. So, but in this particular case, we are saying ignore magnetic leakage and fringing. Now, a BH curve of a mild steel, let us say this is made up of mild steel, then the BH curve would look something like this. In fact, I should, if I want to, it's really symmetric like this. So, it will look it will have a symmetrical situation like this, and what is going to happen is, see, I told you that there are magnetic dipoles and they will keep on aligning as I keep increasing H as I keep increasing H in this direction, more and more dipoles will be forced to align with respect to the applied field, and so the B will linearly initially will tend to increase linearly, but afterwards a saturation effect will start coming in, which is that you do not have to begin with. See, these dipoles are at random. Okay, there would be, if there is some partial alignment, then you will see some initial flux density or some B which is associated with that iron core. It will look mildly magnetic to you like this. When I have not applied anything also, if I measure the B, if there would be some remnant magnetic field intensity which is there, and then as I increase the H, in this direction, they will start getting aligned, and finally it will not matter whether you started from here and traced a journey like this, or you started a journey, you would finally reach the same point when a similar alignment of close to saturation will happen. Now, so therefore, what I am saying is that the slope of the BH curve initially is a straight line, but afterwards as less and less dipoles are available, initially they get a partial alignment. As you keep increasing h, you get more and more finer alignment, and then comes a time when there are no random stuff also left and everything is finally aligned. And when that happens, we say that now the magnetic material has saturated, and once you reach the saturation area, then if you try to increase the current or the magnetic field H, the B will only be increasing, B will only increase with a slope of mu 0, and this is the saturation part where you have delta B equal to mu 0 times delta times of H. But in the linear segment, when it is not saturated, which happens initially, then your delta B slope is going to be mu 0 times of mu r, and somewhere where it starts changing, and different definitions are available, but somewhere where the angle is, let us say, close to 45 degrees, or another definition is project this, project the saturated part, wherever it intersects, bring it down. These points where it comes and intersect, this is called as a knee point, which is to say that after knee point the saturation starts coming in. So empirically you can say that if I want to design a magnetic circuit, I should not cross the knee point, because if I cross the knee point, then I will not get the advantage of using iron, because now the any further increase in B, which typically will happen in a AC circuit, if you try to increase the B, then it will not increase as per mu 0 mu r, but will only increase as mu 0 h. So, it will suddenly, a ferrite core will now start behaving as if it is a air core rather than a ferrite core. That is not what you want to do. You want your things to work in a linear sense here, and so you would try to use it up to knee point, but not more than that. Okay. Now, let us come back to this example. So, the flux density that I want in the central limb is 1.3 into 10 to the power minus 3. Area of cross section of this central core is 800 mm square. So, 800 into 10 to the power minus 6. So, actually I want a flux density of 1.625 Tesla. Now, you have to go to the manufacturer sheet and say, okay, this is the B that I want, then what is the H that I would require? You have to read it from that sheet, and if you read it from that sheet for this particular thing, let us say it comes to around 3800 amperes per meter approximately, then the MMF for the central limb, whose length is 120 mm, it's given here. This 120 mm is going to require you 3800 into 0.12 or 456 amperes is the MMF, ampere turns is the MMF required for the central limb. Now, flux density, let us look in the outer limbs. What are the flux densities in the outer limbs? So, the flux density in the outer limb, first of all, by symmetry, half of the flux will go here, half of the flux will go here. So, the flux will become 1.3 into 10 to the power minus 3 divided by 2, and then the area of cross section there is given as 500 mm square. So, 500 into 10 to the power minus 6, which is around 1.3 Tesla. So, again you have to go to the manufacturer's given sheet for that material and read what cause is H, effect is B, what is the H required to set it up, which is 850 amperes per meter is the H which is required to set up this B. Then multiply that by this distance that it has to travel, which is 850 into 0.3, which is 255 ampere turns is what is required. So, finally, to close this loop, I have to cross through the air gap and reach the central limb again. So, when I try to cross through the air gap, so the flux density in the air gap is same as the central limb, and the central limb flux density is 1.625. This is because I have ignored fringing, and then here in the central limb it is B is equal to mu 0 H. So, H is the B divided by the mu 0. So, it turns out to be 1.292 into 10 to the power 6 amperes per meter. Now, compare these values. You can see how much more H or MMF or current is required actually to set the flux in the flux in the air gap, and that is why air gaps are kept very small. So, I multiply that by 1 mm air gap which is set here, and I will get 1292 amperes as the MMF for the air gap. So, therefore, the total air gap the total current which is required to set up these flux paths is going to be 456 plus 255 plus 1292, which is 2003 amperes. I have been given 500 turns. So, therefore, these ampere turns, these ampere turns have to be divided by the number of turns, which is 500, and I will get a 4 amperes current. So, with 4 amperes current, I can set up 1.3 milliwebers in the central limb. We will take a break here.